Hello everyone, welcome back. And if this is your first time here, you should know that I make videos about whatever I find interesting at a time. And this time it is a connection between mathematics and blood types. Because the other day I got randomly curious about, blood types and decided to Google a table of blood compatibility. And this is what I found. And yeah, it looks interesting, but can you see it? What if I draw these lines? It is Sierpinski's triangle, and you may also know it as the Triforce from The Legend of Zelda. And if you need to refresh your memory about Sierpinski's triangle, here it is. So Sierpinski's triangle is what happens when you start with a triangle and then just start making more triangles inside that one. So for example, if I have this triangle here, and then I just decide to make another triangle inside, this is the Triforce. But then I can just keep going, making a triangle here and here. And so Sierpinski's triangle is what we call a fractal, this infinite figure, right? You could zoom infinitely into Sierpinski's triangle and you would always see the same pattern, the same fractal. Okay, so all of that is interesting, but what is Sierpinski's triangle doing in a table of blood compatibility? Now, your first instinct might be to say that, well, it's just the order. If we rearrange the columns and the rows, then we are not gonna see this pattern anymore. And you are right, but also I think that's kind of missing the point, because the very fact that we can arrange this data to create a fractal pattern means that there must be something going on in here. I mean, these kind of patterns don't appear just because in nature. Every time we see some kind of mathematical pattern in nature, I try to remind myself that there is some kind of deep mathematical insight just waiting for me to understand it. And that's what I want to share with you today. And the first thing that we have to do is just have like a quick overview of blood types. Because okay, so you have probably heard that blood types are like O positive and negative, A and B, but like, what does that mean? Well, it's very simple. Turns out that, at least for our purposes, blood has three different substances. And we are just gonna call them A, B, and RH. And okay, I know if you know medicine, there's a lot of subtlety here and there's a lot of complexity that I'm not going to go over. And of course, these substances have a biological function, but all that we care about is that blood can have these three substances, and you can have them in any combination. So, for example, a person that has a type of blood that is AB positive, it means that this person contains in their blood the following substances. It's A. It's like a molecule or a substance or whatever. I'm not going to worry about too much of the terminology. A, B, and RH. RH is, well, for some reason, doctors decided to represent A and B with A and B, but as you can see, they represent the substance called RH with a plus or minus. And then you can have another combination, for example, AB negative, is what happens when you don't have this RH substance. So a person with AB negative has in their blood just A and B. But then what does O mean? O means that you have neither A nor B. So for example, my type of blood is O positive. And so that means that in my blood, I just have RH. And that's it. I don't have A nor B in my blood. And it's even possible to be O negative. And O negative means that you have none of these three substances in your blood. You don't have A, nor B, nor RH. Now we have to see how this affects blood compatibility. And it is all about the immune system. I'm going to represent the immune system with a white blood cell. And well, cells don't have a brain, so they are not very smart. And so to do their job of keeping you healthy, they follow very simple rules. In this case, the rule that the immune system follows is that if they find something they don't know, they are gonna destroy it. So for example, if you have a person that is AB positive, then their immune system knows these three molecules, A, B, and Rh. And so for example, if they receive blood from someone that is O positive, well, what happens is that the immune system looks at this molecule Rh and they are like, oh yeah, I know that, I have it, and that's fine. But it doesn't work the other way around, because then the immune system of the person that is O positive is gonna see A and B, and it doesn't know these two substances, and so it's gonna attack them, and your body is gonna reject that blood, and you're gonna have a lot of problems. And that's the reason people that are O negative are universal donors, because since they don't have any of these molecules, well, then the immune systems of everyone who receives this blood is not gonna freak out, because there's nothing that would make the immune system attack something, because since there is nothing, there is nothing they don't know. And that's why we have this table. People that are AB positive, they can receive blood from everyone because their immune system knows all these substances, but people that are O negative can only receive blood from other people that are O negative because their immune system just doesn't know any of the other substances. But how does this relate to Sierpinski's triangle? Okay, we are getting there. And to get there, we have to talk about sets. Let's talk about sets, baby. Okay, so what's a set? A set is just, well, it's a bunch of things together, right? So for example, we have the set of molecules that can be in your blood. So for example, we have A, B, and Rh. But since we are doing math, we want to make it more generalized and more abstract. So for example, we can just say this is the same as just having just the set of 1, 2, 3. It's just, all that matters is that we have three things. It doesn't matter how we represent them, okay? So this is a set. And there's also things called subsets. So for example, if I have just 1, this is a subset of the set with 1, 2, 3, because it's just, I just took a part. It's like you just choose, oh, I'm just gonna take the 1 from this set, and that's another set. And from this point on, I'm not going to draw the things here, because as you can see, they are very difficult to draw and look very ugly, but whatever. Then I could choose, let's think, what are all the possible sets that we can make with just 3 elements? For example, we could choose only the 2. That's another set. We could choose only the 3. That's another set. Oh, but before that, we can choose 1 and 2. That's another set. And we could, and 2, 1, this is the same as having 2, 1, right? Because it's just the same. All that we care are the elements. We don't care about what order they are in, right? But then we can have the 3, and we can choose 1, 3, and 2, 3, and 1, 2, 3. But there's one more option we haven't considered. What if we were like, well, you're not my boss, I'm not gonna choose anything, I don't care, I'm not gonna make any subset. Well, guess what? That's also a subset. When you have like what we call it the empty set, that's nothing. That's also a subset. You can make it from any other set by simply not doing anything. So in math, even if you're lazy and you don't do anything, you're still doing something, kind of. And even mathematicians have a special symbol for this, for the empty set, because I guess drawing these things is too hard. So this is the same as this. I'm gonna represent it with this symbol, just a 0 with a slash. And now that we have all the possible sets that we can make with 3 elements, this is what we called the power set. Okay, so all these elements are the power set of 1, 2, 3. And there's also something really interesting, like if you remember that, well, this is the same as having the blood types, 1, 2, 3, like 1 is A, 2 is B, 3 is Rh. Then, for example, the empty set is O negative, because it's having none of these molecules. And then 2, 3 is, let's see, if B2 is B and RH is 3, this is B positive. And you should always be positive. And 1, 2 is, 1 is A, 2 is B, so this is AB negative. And in general, these are all the blood types. And so we can say that, oh no, that's not this one. Now we can say mathematically, we can look all fancy and say, well, the blood types are just the power set of the molecules A, B, and RH. So that's fine, that's interesting. But how does this relate to Sierpinski's triangle? I'm getting there. Let's look now just at this blood type, B positive, which we are representing with just 2, 3. So this is just the set 2, 3. And remember, 2, 3 is a subset of the set 1, 2, 3, okay? But then we can say like, well, what are the subsets of this subset? What are all the sets that we can make with just these 2 elements? Well, that's easy. We can just choose the 2. We can just choose the 3. We can choose both the 2 and the 3. And finally, we can choose none of them. And what blood types would this be? Well, I'm gonna write them here. You're gonna see why. So in this case, this 2 is just someone that has only B in their blood. So this is B negative. This would be O positive. This would be B positive. And this would be O negative. But now check this out. If we look at the row for B positive and we look what kinds of blood it is compatible with, it is compatible with O negative, which is this one. It is compatible with O positive, which is this one. It is compatible with B positive, which is this one. And is compatible with the B negative, which is this one. So we can say that in order for blood types to be compatible, they need to be subsets of the blood type of the recipient. Okay, so that's very cool because we managed to put into mathematics this law of nature. Because remember, this all comes from just the immune system having this one simple rule. But how does this relate to Sierpinski's triangle? Well, we are finally there. Let's look at this. So let's first simplify this, because that's what you have to do with mathematics. First generalize, then simplify. We have generalized, and now we're going to simplify it. Imagine that there's some kind of animal, some kind of species, and in this species, they only have one molecule in their blood. So, and we are going to call it A. So they can have either a blood type that is A, or what we would call O negative, which is like nothing. Or like, in this case, it would be just O. I'm just going to represent it with a symbol for the empty set. And then what would be the table for blood compatibility for creatures of this species? Oh, because let me tell you something. Other creatures like cats, dogs, horses, they can have a lot more molecules in their blood. So we humans got it easy. So let me check something. Okay. So for example, let's say we could have donors in this species of animal that don't have any molecules in their blood, and then, well, they do have molecules in the blood, but for our purposes, they don't have any of these molecules, or they could have this A molecule, and the recipients could either have this molecule or don't have it, right? And remember, like, we are gonna use our rule of subsets. So for example, is the empty set a subset of the set containing just A? Yeah, of course, you don't choose anything, and that's how you make the empty set. Can you make the empty set with the empty set? Yeah, of course. Again, you just don't choose anything. In this case, there's nothing to choose, but still. So it's also compatible. Can you make the subset A with A? Yeah, of course, there's only one element, so just choose that one. Okay. And finally, can you make the subset A with the empty set? Oh, no. Here you can't. Interesting. So this would be the table of blood compatibility in this species. But what if, I don't know, there's a mutation or something, and now there's another B molecule? How would the table look now? Well, now we would have creatures that don't have any of these molecules. They can only have A or B, or they could have both of them, right? And again, you could donate it to creatures that have all these things. And we just apply the same rules we have discussed to see how this would look like. And here is where the magic happens. Here is where we get our deep mathematical insight. Check this out. First, let me choose another color. First, here we have our triangle, okay? And then here we have triangles as well. And this is happening because the blood types in each of these triangles have exactly the same relationships as in this table. So let me show what I mean. Let me go back to white. So for example, let's look just at this part of the table. So we have AB and B, and we are seeing their compatibilities with B or AB. And so, okay, so of course B is compatible with AB, and AB is compatible with AB, B is compatible with B, but AB is not compatible with B because it doesn't have A. But now, look at this. Do we really need to have B in here? Because what happens if we just replace in this table B, the symbol of B, with a symbol for the empty set? And here where we have AB, we just delete it entirely. So we have this exact same table again. Look, we have empty set, A, empty set, A, empty set. And the same happens with all of these tables. For example, in this case, we would have to delete, again, if we just delete B and replace it with the empty set in this other triangle, we would get again this same table. And then, and this is when you have just 2 molecules in the blood. When you have 3 molecules, it's just the same thing is happening all over again. Everything is made of just these tiny triangles. And all these triangles happen when you just replace with the empty set everything they have in common. And then you just look at the things they have in difference, I guess, and you get this table. So this one table, the one with just 1 molecule and the empty set, is like the fundamental table. And it's just getting repeated over and over and over, all over the place. So this is why we are getting Sierpinski's triangle. We are getting Sierpinski's triangle because it all comes from just this one fundamental table. And then every time we add another molecule, they are just keeping the same I mean, there are more molecules, but the relationship, the rule is still the same. And so the same thing keeps happening over and over and over, forming all these groups of triangles. And that's amazing because it's not the Sierpinski's triangle can look like something that is very complex, right? Like you look at it and you are like, someone definitely thought about it. Like it looks like made with purpose. But we have seen how the immune system, following just one simple rule, attack everything you don't know, creates it. And in fact, like for example, we can see that it holds, of course, if there are more molecules. In this case, this will be the blood table compatibility for a species with 4 molecules in their blood. And if you look at it, it's very cool to see that this table in here, this little triangle, is just this whole table. Because like you have all these small triangles here, and so those are the same triangles you have here. And it gets repeated 3 times. well, here, and it gets, and so every time you add another molecule, you just take the previous table and just repeat it 3 times. And that's amazing. And this holds for any creature on Earth that one has blood and whose immune system follows the very simple rule: attack everything you don't know. That's all you need. Now, I tried to look for the blood table compatibilities for dogs, cats, or other animals, but turns out that they are not very well researched. We don't even know how many blood types there are in dogs. Like, one was recently discovered. And yeah, and there could also be like, maybe their immune systems don't follow this exact rule. Maybe they, for some reason or another, follow more complex rules. So that's kind of disappointing, because I wanted to show you the tables for blood types of many different species and show you the same pattern. But I guess we need to be sure how many blood types there are in dogs and horses and cows and many other animals before we can produce this. But still, it's very cool to see how this is just order, a pattern that arises from just following very simple rules. But there is one last thing. What about the order? Because as we discussed at first, if we change the order of the rows and the columns, we are not going to get this pattern. We are going to get something different. And I don't have like a very deep mathematical insight as to why we should use this exact order, but it is very logical once you know how to make it. So let me show you. So for example, let's say that you have the following elements, 1, 2, 3, and 4. This is how you produce the order for this table. You start, of course, with the empty set, and then you choose 1. And then you have nothing else to do, so you choose 2. And then you combine 2 with the previous element, which would be just 1, 2. And then you choose 3. And sorry, I don't know what happened with that 3, it looks horrible. And every time you add a new element, you just combine it with everything that appeared before. So for example, if we combine 3 with 1, we have 1, 3. 3 with 2, we get 2, 3. 3 with 1, 2, we get 1, 2, 3. And then we add 4. And then we just do the same. 4 with 1 is 1, 4. 4 with 2 is 2, 4. 4 with 1, 2 is 1, 2, 4. And then I go here because actually use the whole thing. I'm going to access. And then I combine 4 with 3 and we get 3, 4. And then we combine 4 with 1, 3, so we get 1, 3, 4. Then we combine 4 with 2, 3. I forgot the idea, so 2, 3, 4. And then finally we combine 4 with 1, 2, 3. And we get 1, 2, 3, 4. And if we add 5, like it would be the same thing. We would combine 5 with everything that appeared before in the order that it appeared. And so, yeah, this seems like a sequence that is very easy to make, and it's also very logical. So, and I'm sure there must be some more mathematical insights to be had as to why this sequence is important. But at some point, like, I'm not 3 Blue 1 Brown or Bihart. Obviously, if they saw this, they would have a lot more insights about this. But sadly, about this sequence, all I can say is that it's very logical and it's very easy to make once you know how to make it. And if there is something I want you to take from this video, is that every time you see some kind of pattern in nature, remember, there is some kind of mathematical insight you could have. There is math hidden there and is waiting for you. And so you just have to look for it. And when you find it, it's really satisfying to see how order arises in the universe. And well, that's it for today. Thanks for watching. I'm gonna put you some videos here from that the algorithm thinks you're gonna like. And if you like, please subscribe and give me a like. Thanks. Goodbye.